This lesson will focus on something called graphical modeling. We talked up to this point about graphing and about the scientific method and how to come up with models that explain certain phenomena we see. This lesson will focus on how we take graphs and determine relationships from them. And that process is known as graphical modeling. The goal of graphical modeling is to look at variables that we have graphed and be able to determine a relationship just by the shape and structure of that graph. When looking at any sort of graphs, when looking at the relationship, we can really break down any sort of graph into 5 simple relationships. The first one is no relationship, that when we graph something there is a clear no relationship between the variables, meaning one variable did not affect the other. Then there's a direct relationship, inverse, a square, and a square root. Okay, and then one of the last things you may see is that you may also get a combination of some of these. You may graph one that looks maybe like a square, and then after doing some sort of manipulation you may see that, okay, now it's something else. Maybe it's an inverse. Okay, and then doing that, then we'll see that there's a combination of both a square and inverse relationship. Okay, and the whole point of this is taking these graphical models, these graphs, and then what we're going to do, the next step, is to come up with a mathematical model. So the graphical modeling is a step in what we're normally going to do in order to get a mathematical model, which is simply an equation. Alright, the first type of relationship, which I already stated, is a no relationship. This one is defined that when changing the independent variable, and again, recall the scientific method that we always change the independent variable to see how it affects the dependent. In this case, changing the independent variable will have no effect on the dependent, meaning that they're not related. Okay, so looking at this type of relationship, if we thought that, for example, here in this graph, that the mass was one of our independent variables, and we wanted to see how it affected something called the period, which is a measurement of time, notice we get a horizontal line. Now, if you think what a horizontal line means, okay, starting at 0, 0, in the x-axis, our mass is saying as I increase my mass, okay, I'm increasing mass by going to the right, the period is not changing, it's staying at about 2 seconds. So changing the mass keeps the period constant, does not change it at all. So there's no relationship. So where we may have thought that the mass would affect the period, looking at this graph, it would show that's not. So anytime you see a horizontal line, that means there's no relationship between the variables. There's no effect. The second type, and the most important type of relationship that we'll see, and this is really the easiest one to use and to see, is called a direct relationship, otherwise known as a linear relationship. A direct relationship says that when you change the independent variable, whether increasing it or decreasing it, it has the same effect on the dependent variable. Right? So looking at the graph we have here, increasing what's shown as time squared, increasing the time increases x, which is what we'll call position. So increasing time increases the position. So both these have the same effect. So as you go from 0, as time goes up, your position increases. Okay, so that's showing a direct relationship. The same thing would be shown in the opposite, is that if I decrease x, I'll decrease y. It's kind of going back this way. So if I decrease x, I'm also going to decrease y. So it really shows the same thing. Okay, you can also see linear relationships or direct relationships that look like that. Okay, a line that looks like this, that's also a direct or linear relationship. Just has different sort of meanings to it. And again, the direct relationship is the simplest relationship we can have. It's a straight line. All right, and you'll see that when we get to graphical and mathematical modeling, our goal is to always get a direct relationship. This is the most important one that we can have, and we'll discuss this a little more further when we get to it. The third type of relationship that you could see is an inverse relationship. An inverse is somewhat opposite to a direct relationship. What this shows is that as you change the independent variable, whether increasing or decreasing it, it has an opposite effect on the dependent variable. So increasing the independent variable will decrease the dependent variable, or decreasing the independent variable will increase the dependent variable. So they have opposite effects. All right, and this is shown here, you can see in this graph. This graph is a graph of an inverse relationship. see that as x increases, as we start from 0, as we increase x, my y values tend to decrease towards 0. Okay? An inverse relationship is also asymptotic. Okay? It has an asymptote with the y-axis and with the x-axis. But the key thing here is that as x increases, the y variable is decreasing. And that is an inverse relationship. Okay, the next type of relationship is a square relationship. And if you think of an equation, it would be something of the form of y equals x squared. Right? So a square relationship. This is showing it's similar to a direct relationship in that when you're changing the independent variable, it has the same effect on the dependent, meaning it's going to increase the dependent if I increase the independent. Okay? So increasing one will increase the other. However, with a square relationship, all right, we also have an exponential effect on it, meaning that as I increase the x variable, the y variable is going to increase, but it's going to increase at a faster rate as we go on. Okay, so that's where we get that exponential effect. The graph that you can see is obviously shown here, that as x is starting to increase, y is also increasing, but notice that it starts to lose its direct relationship and start to curve upward. That's obviously a y equals x squared relationship. Okay, so you're having the same effect, but there's a greater effect on it, a more exponential effect. The last relationship that we could see in this class is a square root relationship. This one is shown below, and what happens is that changing the independent variable has a similar effect on the dependent variable. But with this one, it kind of has a different effect as compared to a square relationship. Notice the graph below, that if we take our x variable, our independent variable, which is time, and show that that is increasing, what we see with the dependent variable, or the y, is that this also tends to increase, but notice as time goes along that the rate at which this increases tends to slow down. So it increases at a slower rate as time goes on, or as the graph goes on. And this is seen as a square root relationship. All right, a square root relationship is also known as a y-square relationship. If you were to take this graph and rotate it such that your y-axis was your x, you would see that this also looks like a y-squared or a square relationship. Okay? Whereas if y is increasing, x is going to increase at that rate. Okay, so a square root relationship, a y-square relationship is the same thing. If you think of a function, this would be of the function y equals the square root of x. And if I think of, okay, where am I getting this y squared from? Well, if I want to get rid of this square root, all I have to do is square both sides. Okay? Square of a square root is whatever inside the square root, which would be x, and then that would leave the other side as squared. So a square relationship is also shown as a y-squared relationship. But the way you tell this is, again, it produces the same effect, increasing or decreasing, but what you tend to see is that the rate at which it increases or decreases tends to slow down a bit. So given these 5 graphs, the whole point of this graphical modeling is that when we do a lab and we gain information on variables and then we graph the relationship between those two variables, we are going to come up with a graphical relationship. And what our goal then is to be able to tell ourselves, just by looking at the graph, what is the actual relationship between the variables. And we can state a general relationship saying, like, for example, that, okay, x and y are directly related, or x and y are inversely related. That's going to give us, one of those 5 basic relationships between the variables. But the next step in this process then is, once we know the graphical relationship, what we then want to do is come up with a mathematical relationship or a mathematical model that explains the relationship between those variables. And when I say that, a mathematical relationship or model is an equation. So we're going to come up with an equation from that graph. And then, in this class, physics, we're going to use a lot of the equations, such that we can plug in general numbers and general variables, and it's going to give us some output, something that we can then use. So we are actually going to come up with the graphs, and we are actually going to develop the relationships and equations we are actually going to use in this class. So every equation that we're going to use is something that we're going to develop on our own. And we're going to use that basically from the graphs. And our next lesson will focus on the mathematical modeling portion of this. Right now we're going to focus on the graphing. But the thing to always keep in mind is that the simplest relationship that we can use is a direct relationship. Okay? And what we want to do is get a equation from that graph. And we're going to talk about this more, but with a direct relationship, the one thing to remember is that if we think of an equation, this is going back to math class, the equation of a direct relationship is of the form y equals mx plus b. And our goal is to always take a relationship and write it in this form, okay, of the slope-intercept form. And we're going to gain relationships from things like the slope and the y-intercept, and then we're going to be able to use these equations and derive meaning from them. So the whole point of this graphical modeling is to be able to understand a relationship and then be able to use that to formulate an equation. What we're going to do right now is look at how we take a graph and determine the relationship from it, and then I'm also going to show you a technique in which we can take that graph and that data and manipulate it such that we can get a direct relationship. And like I said on the previous slide, once we have that direct relationship, then we can formulate an equation in the formula of y equals mx plus b. Alright, so when looking at our data, the first thing that you hopefully should be able to do just by looking at this lesson is be able to compare whatever graph we have to the 5 relationships I showed you. And then we're going to try to determine what type of relationship that is. And starting with that relationship, that basic relationship, that's going to help us to determine what is the actual equation or what is the mathematical model that we're going to receive from that relationship between the variables. So when you get a graph, when you graph data and you get just the simplest graph that you have, there's 2 things that you need to ask yourself. The first, the simple question, what is the shape of the curve, or what is the shape of the graph? And the shape of the graph is going to represent the relationship. So is it a direct relationship? Is it a straight line? Is it a horizontal relationship? Do I see a horizontal line? Is it an inverse relationship? Is it a square? Is it a square root? You're going to look at the graph and determine, just by the shape of that curve, what is the relationship between the variables. And our goal then, once we understand the relationship, is to be able to get a direct relationship. That is one of a straight line that looks like that. So that is our goal. Once we get this relationship, then we can put it in the form of y equals mx plus b and get an equation that we can then use. So, how then can I change one of the variables to get a direct relationship? Now, with this process, you always have to remember that when we do any sort of manipulation with data or in a laboratory, we always change the independent variable. We never change the dependent. So the same thing is going to occur here. If I see that I have, for example, an inverse relationship, all right, what I am going to do is I am going to change the independent variable that represents the type of relationship I have. Meaning that if I see I have, for example, an inverse relationship, what I am going to do is I am going to manipulate the independent variable such that it will give me a direct relationship. What I mean by that is that I see that it's an inverse relationship. What I'm going to do is I'm going to take all my independent variable data, that means all my data for x, whatever it may be, and I'm going to take the inverse of every number that I have. And I'm going to now have new data that's going to be the inverse of that, the inverse of x. Then what I will do then is graph my modified data, which is the inverse of x, versus the dependent variable, which I have not changed. Remember, you always change the independent variable. And from graphing the modified data versus the dependent variable, you should, in most cases, get a direct relationship. And then from that, we will then be able to write a mathematical model, i.e. an equation, and then be able to use that equation. The process I just discussed about graphical modeling and being able to manipulate data and graph modified data is a very difficult process. But it's also something that's very powerful. And after going through a few examples, you'll see that it's not the most difficult thing to do. And it's very useful when we get to labs and get to other things. It's a very useful tool to have in any sort of science classes, be able to understand relationships and then be able to come up with a mathematical model or an equation based off of that relationship. So let's do an example of this now. Okay, we're going off of worksheet 5, number 2. Okay, it's a graph of x, which represents position, and time in seconds. So what I'm going to first do, let's just kind of review. We talked about graphing in the last lesson. So let's start by looking at this data and actually graphing it, following the proper rules of graphing. So we will assume that the independent variable will be time, and our dependent variable will be x in meters. So following our rules of graphing, the first thing I need to do is I'm going to label my axes. So my independent variable always goes on the x-axis. So time in seconds is going to go on the x-axis, and x in meters is going to go on the y-axis. Okay, then I'll also put a title on it right away. I have, and remember, title is always dependent versus independent. So I'll have x in meters versus time in seconds, and this is the graph I'm representing. Okay, so now looking at my data, I want to be able to graph this, so I'm going to check my data and I'm going to choose a scale. I'm going to start at 0, 0. Okay, for my scale, let's start with my x variables, or my time in seconds. Okay, so I start from point 1, I go to 5. So what I'm going to do is I'm going to go by point, I'm going to choose a scale of 0.5, or I'm going to show that every 2 boxes I have 1, so I'm going to go 1, 2, 3, 4, and 5. So my scale is 0.5 because every box represents a half. Every 2 boxes would be 1. Then looking at my dependent variable, I go from 0.03 to 75. Alright, so I'm going to choose a scale of 5. So starting at 5, I go 10, 15, I'm going to skip a few now, 20, 30, 40, 50, 60, 70, and then notice my top box there would be 75. Okay, so I chose my scale. I have a constant scale, there are no breaks in the axes, and now the next step then is to plot the points. So I'm going to start with my time at 0.1, my x in meters at 0.01, so this one is going to be very close on my graph to 0, 0, as best as I can. Next one, 0.2 and 0.12. Same thing, 0.2, barely moved in the x, so they're going to be almost right on top of each other. Again, it's just kind of tough to see. I'm plotting my points if you guys can see it down here. Next one, I go to 0.5, which is right on this line here, and I go up to 0.75. So it's going to be up a little bit and right on that line. Then next I'm at 1 and 3. It'll be there. Then I'm at 2 and 12. So now I'm starting to see where the points are. 3 and 27. So that would be right there. 4 and 48 would be all the way up by 50. And 5 and 75 would be up here. Okay. So now if I look at this graph, next thing I want to do is interpolate the points. That's drawing a smooth line of curve between the points without going past. So drawing that curve, trying to follow the path of the data but not just connecting the dots, I get that sort of graph. Alright, now once we get this graph, here's the next step. I want to determine from this graph what is the relationship between the variables. So looking at this graph, okay, graphing it correctly, you see that, okay, it shows a relationship. So what is the relationship? So I'm going to compare it to one of the 5 relationships I just talked about. Okay, so that was a no relationship, direct, square, a square root, and an inverse. So looking at this graph, I can obviously see that it is a square relationship. Meaning this is of the form y equals x squared. If I were to connect this graph and on the other side, you would see that it formed that type of relationship, a square relationship. So, taking this information, the square relationship, what I'm going to now do is I'm going to modify the independent variables to match this relationship. Meaning I'm going to take all my x variables, my time variables, and I'm going to square them. And I'm going to get new modified data that's going to represent that relationship. So, once I know the relationship, we said that it was a square relationship. The next step that I'm going to do is I'm going to now modify my data. And I'm going to modify the data such that it represents the type of relationship we have. This is where the tricky part comes into play. We said it was a square relationship. We showed that the graph looked like that. A square relationship is an equation of the form of y equals x squared. Notice in this equation I have my x variable, which is the independent variable, is squared. What I'm going to do is I'm going to perform the operation on the independent variable that matches this relationship. Okay, it's a lot of fancy jargon. Basically what I'm going to do, this relationship is y equals x squared, so I'm going to take all my x variables and square them. Okay, so what are my x variables? Well, we said the independent variable in this case was time in seconds. That represented my independent, and my dependent was x in meters. So I'm going to take all my independent variables and I'm going to square them, such that I get a new column where I have time squared with new units of seconds squared. I'm going to take all my times and I'm going to square them. And I'm going to get a completely new set of data shown in this column here. So let's go ahead and square all of our x values. So 0.1 squared will give me a value of 0.01. 0.2 squared will give me a new value of 0.04. 0.5 squared will give me a value of 0.25. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. Okay, so all I have done is I have taken my independent variable and I have manipulated the values such that they represent the type of relationship I have. Okay, so all we're doing is modifying the data. If you think of when we talked about data, there was raw data versus generated data. This new column would be an example of generated data. We're not really manipulating, not changing our raw data. All we're doing is just performing a mathematical operation on it. So this is still okay to do. And now what I'm going to do is I'm going to graph my new data. Okay, again following the rules of graphing. Now, I have not changed my dependent variable, so my dependent variable x in meters still stays on the y-axis. Now, I modified the independent variable, and now my independent variable is no longer time in seconds, but it's time squared with units of seconds squared. So now I am graphing my modified independent variable, not my original. Okay, and now graphing should be relatively easy. Now we got to go back. Okay, I'm going to choose my origin at 0, 0. Before I do that, let me just put a title on. So dependent variable x in meters versus my new independent variable, which is time squared with units of seconds squared. Okay, so I'm graphing my dependent versus my modified independent. Okay, now we go with choosing scales. So, my x variable, I have values of 0.1 or 0.01 all the way up to 25. Okay, so what I'm going to do is choose a scale probably of 5, for example, would probably be an easy one. So I'm going to choose a scale of 5. So choosing a scale of 5, let me label my axes. So I'm going to start here, I'm going to go 5, 10, 15, 20, and 25 there. Okay, and then for my y, notice that I haven't changed any of my dependent variables. I haven't changed any of the y variables, so my scale is going to be the same as it was. Okay, we went by 5s. I'm going to draw it every 10, so 10, 20, 30, 40, 50, 60, 70, and that last box up there would be 75. Okay, so now that I manipulated data, now I can plot the points, and I got all my scales and everything drawn, so let's plot the points. Okay, so plotting the points, I'm going to start off, I have 0.01 and 0.03. So this one is going to be relatively close to 0. My next one I have 0.04 and 0.12. Again, that's going to be pretty much right next to it, a little up more. Then I have 0.25 and 0.75. So we're going to increase very slightly. And then I have 1 and 3. So I'm going to try and do this the best I can. We're kind of close, so it's tough to see. Alright, now we can see a little bit better. I have 4 and 12. Okay, so 4 and 12. 4 would be here, 12 something there. Then I have 9 and 27. So 9 and 27, something there. And then I have 16 and 48. So 16 up to 48. And lastly, I have 25 and 75. Okay, now if you look at this, it's a little easier to see. You can see that we have something that's forming a straight line. So if I were to interpolate the data, I'm going to do it with a red line here. We can see that when going from our initial point all the way up to the top, if I were to draw a smooth line that interpolates the points, not necessarily connecting the dots, notice that I get a straight line or a direct relationship. Okay, so voila, I have a direct relationship. And that is what I want. And now that I have a direct relationship, what I can do is I can take my variables and I can write it in the form of y equals mx plus b. So now I can write an equation from it, a simple equation. And then once I know that equation, I can use it. Whereas I can plug in a value for x, and it's going to poop out a version of y. It's going to give me some value that I can then use. Okay? So what we've done is we've taken data, we've modified it, we graphed the new modified data, and we then saw that we got a direct relationship. So again, notice that when we get a direct relationship, we get now an equation, the simplest equation we can write of y equals mx plus b. And then once we have that equation, then we can fill in our variables and what we have, and then use that equation. And that's kind of the next process of mathematical modeling. Is once we go through this process that we just showed called graphical modeling, we're going to get an equation, then we can use that equation and then plug in random values of anything we want, and it's going to give us something that we want to know or want to find out. Okay, so the process we talked about in this lesson is called graphical modeling, and this kind of leads into the next step of mathematical modeling.